evening, actually. Can you hear me and can you see my screen, I suppose?
Yes.
Slide? Okay, fine.
Yes.
Okay, then the goal of this presentation is to basically present to you what we are carrying out inside the Comfort Drones project, already presented, about model-driven simulation and performance analysis of systems based on ROS and very particularly systems using drones. Then the presentation is basically divided into 3 parts. Then the first one is the introduction, where I will try to convince you that this piece of work is worth to be carried out. Then I will describe the approach we are following in model-driven, providing the system engineer with model-driven design capabilities for ROS-based systems, addressing complete services based on drones. Then I will describe which are the objectives, the technical objectives we want to achieve. And then I will present to you the first preliminary results we have achieved. Finally, some conclusions will be derived. Not necessarily to convince you about the power of model-driven design. It's a way to elevate, to go to higher abstraction levels. And it's a very mature software engineering methodology with several very well-known already working, like MATLAB Simulink, AMESIM, Cofluent, or Ptolemy 2. As you have probably realized, I have concentrated in those environments where you can model but also simulate, not only model the system itself. In this domain, the main standard is UML. UML, it's very open, probably too light in syntax, but anyhow, it's a very natural way to capture any system architecture, and at the end, any engineering project starts by identifying the different pieces and how the different pieces interact each other. These pieces can be hardware pieces, software pieces, many other concepts. And this is what UML lacks, this ability to, in many cases, make clear, okay, this component has to be understood in this way, and therefore should be treated and should be handled in that particular way with that particular purpose. In order to cover this lack, several domain-specific profiles are proposed and are being used. And there are some frameworks like Metamorph, where you can work, define the different profiles and work with them. And something which is worth to be mentioning here is the design gap between model-driven design tools based on UML, for instance, and electronic system level tools, where you will work in C, C++, you will use VHDL, you will use virtualization in order to simulate the software on concrete platforms, etc. There is a gap moving from one model, let's say, one framework to the other is not so simple. This is the gap we would like to cover. The background technology, it's S3D, which is component-based, based on a required provided services paradigm, client server paradigm. And the goal we would like to achieve is to extend and this background technology to cover ROS-based cyber physical systems of systems. The idea is to be able to model the complete service using concrete DSL, which in our case it's an extension of Marte. Being able to specify the functionality using different languages, for instance, in C, C++, and then allow the system engineer to analyze the properties of the system with in regards the different concerns which are relevant in this particular application domain or in this particular project. Performance, safety, cost, security, etc., etc. Let's try to include in this single model whatever information is relevant in this particular project, and only when you have analyzed all the different implications and you are fully convinced that the system is going to behave as expected, then because you have already extract from this single model the information you need in order to perform the different analysis techniques, like for instance schedulability analysis, simulation verification, etc. When you are completely convinced that it's going to work, then you can extract again the information from the single source model and generate the software stack to be executed on these distributed heterogeneous platforms on which services are being deployed currently. And at that time, it's when you will introduce the middleware and the real-time operating systems you may need in each case, like for instance ROS. As I have commented before, we want to extend this technology to the ability to cover systems making use of drones. Then the concrete objectives we want is to support reusability and legacy ROS code support, then extend this framework with modeling of ROS-based systems, support simulation and performance analysis at different abstraction levels, so that at the end you can be as close as electronic system level information you may require, then support fast design space exploration, and finally software synthesis. Reusability is already something that is addressed by S3D, and in order to support or to extend that to ROS-based systems, what we have allowed is to link the different components not only to C, C++ as main programming language, but additionally to ROS, most concretely ROS CPP. Then we want to apply our component-based client-server modeling methodology to ROS systems. And one of the difficulties we have found here is this interoperability between published subscriber modeling paradigm, which is supported by ROS, with a required provided paradigm or client-server paradigm, which is the fundamental supported by S3D. Our experience here is that this client-server modeling paradigm is, let's say, more abstract, therefore more interesting in principle for us, so that from it you can generate the ROS implementation if needed and when needed, while the opposite direction sounds much more difficult. Okay, then this is the kind of systems we want to support. System composed by different components hierarchically, because any of these components could be a subsystem by itself, and the main part of main functionality will be probably modeled in C++, while there will be some components linked to ROS CPP code. That means that part of the component will follow this client-server communication and synchronization paradigm with the rest of components of the system, while there will be some interfaces related with ROS functions, which apparently may go to a different component, and this is not really the case, because there is the ROS infrastructure in between taking care of all these communication mechanism. This is the toy example we will use, very simple example, which is running. I mean, it's executable. It's there is code inside the different components, so we can simulate it with load work model, while the functionality is very simple. I mean, it's only implementing very simple cases. There is an actor, and this actor will buy through a portal a particular good. Once the payment is ensured, then the good should be moved, and the good available, of course. The good should be moved to the address specified by the client, and then this final destination, it's analyzed by a road generator, and the road generator will provide a flight plan to the delivery central, which will select a particular drone and will send it this flight plan in order to take the good, follow the flight plan, and deliver the good in the corresponding place, and then come back, of course. We want also support simulation and performance analysis at different abstraction levels. And then to do that, we have to generate a test bench for the application. In our case, a C++ model of the client, and here a model of the drone, which will be a very simple autopilot or a complete autopilot simulation model. Then as an initial, let's say, verification point, we will perform, we will provide the system engineer with pure functional simulation. That means that we want the simulation time to be as short as possible, therefore the simulation be as fast as possible. And in that case, this model of the autopilot will be extremely simple, as simple as you want. Just starting the flight, then eventually moving to a particular height at a constant speed, then following the flight path as an additional or different horizontal constant speed, and coming back, something like that. Of course, simulation time, it's will be different than simulation time, simulated time, sorry. Eventually, simulation time much slower or smaller, sorry, than simulated time. And our simulator is VP. And in order to achieve this goal, we have to separate ROS from the timing calls to the operating system, Linux, and take control on how the time is evolving in all the ROS code. Okay, this is the idea, and also for the client, a very simple C++ model. Regarding this ROS, the system model combining C++ and ROS code. Here we have also some different abstraction levels. The first one will be a load model, which is the one we will apply here. But also when the full code is available, then we will be able to perform native simulation, which will provide to us much accurate performance data. And finally, and only when needed, of course, a complete virtualization system is possible. This is the technology used by electronic system level tools like Synopsys or Cadence in order to provide, to bring to you a more detailed performance analysis and more accurate data. The simulation infrastructure in that case, it's everything under the control of VP, because not only the test bench, but also the system is C++ and ROS CPP. And the only point to comment here is that, of course, this simple drone model has to be able to understand this and to simulate correctly these ROS function calls. The second level would be cyber physical, as fast as possible simulation. Again, simulation time, it's different to simulated time. Again, simulation time as short or small as possible. The client can be handled in the same way as before. The code is going to be the same and handled again the same way, but in order to model the copter, we will introduce a complete autopilot and analog simulation model, in our case, Arducopter and Settle. The simulation infrastructure is different in that way, because now the drone simulator, it's again, it's Arducopter, it's again under the control of BP, like all the C++ and ROS CPP code. But this code now, it's linked with the drone simulator through MAFROS, and the interaction between the model and this drone simulator is made through ROS core. It's VP taking control of the synchronization clock that make ROS execute without the timing of the underlying operating system. And the final simulation model will be a cyber physical real-time simulation of 1 second per second, in the sense that real-time and simulated time and simulation time will be equal. This will allow us to handle the drone directly. Again, of course, the system can be executed or simulated just with a load model using native simulation. And in that case, virtualization will be much more difficult to be used because the simulation speed is slow, and very probably putting it in conjunction with an analog simulation here for the drone will make the simulation time even slower than the simulated time, which it's not desirable in general. If we have enough computation power, then we could also or even add 3D software graphic interface. Okay, the two final objectives were fast design exploration and software synthesis. The idea is to provide the system engineer with the possibility to select different architectural mappings, because in S3D you can specify the platform-independent model, but you can also model the platform, the hardware platform. In our case, we are considering 3 different nodes. The first one is the fleet of drones. The second is the control station in direct contact with them. And eventually, there is also a cloud server providing this web portal to the clients. It's clear that this concrete model, the road generator, can be either implemented in the control station, like the client, the delivery software, or in the case of the delivery software, move it to the cloud. Regarding the drone controller, it can be implemented in the control station or directly in the drone, which would require an additional board, eventually with more weight, with higher power consumption, but with much less communication movement between the control station and the drones. The very preliminary results with only one drone we have achieved are the following. The functional simulation can be as fast as 610 seconds per second. The percentage of CPU it's taken by the VP kernel with 81%. That includes also the drone simulation model, the drone model. This very simple model of the drone I have mentioned already. By using quadcopter and SITL, or quadcopter and gazebo instead of SITL, simulated time and simulation time almost are equal. Probably still a bit higher, which means that we're going faster than real time. Most of the time, as you see, it's taken by ROS in both cases, by the ROS core, MAF-ROS, and the drone simulation, which is, in that case, it's quadcopter or with SITL, or quadcopter with gazebo. And very small in the case of VP, with give us the impression that okay, there is, even including civil physical simulation, we have some, let's say, place for much more complex system code, particularly because the machine on which these experiments has been made, it's not a very powerful one. Okay, just to finish, we have work in complex distributed services, which we think demand of new civil physical system of system design methods and tools. And particularly, our goal is to extend S3D in that direction in order to model and analyze and design drone-based services. Model-driven system design, it's a powerful candidate to achieve that, and therefore S3D, it's a good candidate tool in that direction, supporting mega modeling and supporting simulation and performance analysis, so that we can explore different architectural solutions and select the most appropriate. Preliminary results we have achieved so far are encouraging in that direction. Okay, thank you very much for your attention.